you already know that sound travels at a finite speed. It travels at a speed that you can sense for yourself. And of course, if you want to, you can go about measuring it. It's really quite simple, particularly if you use echoes. You find the side of a large barn or a cliff on a fairly quiet day, stand a few hundred yards away, clap your hands sharply, measure the time it takes for the sound to come back to you, and then measure your distance from the reflecting surface. A water ripple makes a good model of an echo. Well, if you do this a number of times, you'll find that in air, sound travels a little more than 1,100 feet per second, or about 340 meters per second. Now, an echo is simply reflected sound. In order to find out whether the angles for reflected sound obey the same law that we found for reflected light, we're going to need a beam of sound and a suitable laboratory in which to use it. Now, this studio is not an ideal sound laboratory, but we have taken a number of precautions here to minimize the stray reflections. For example, these are glass fiber blankets that absorb most of the sound that strikes them. And the floor is covered with thick felt pads. Without these precautions, we wouldn't be able to separate the sounds we are going to study from the many extraneous reflections from the furniture, the ceiling, the walls, and the floor. Now, our sound is going to be produced by this equipment over here. We'll generate the tone in this oscillator. And we can have a range of higher tones or lower tones. And, of course, we can also adjust the intensity up or down to suit our needs. Now, the electrical output from this oscillator is amplified over here, and then it activates a loudspeaker driver. And the sound produced in this loudspeaker driver is fed into the throat of this horn. Of course, we could just hold the loudspeaker driver out in the open, but then the sound would go out in all directions like the light from a candle flame. When the driver is attached to this exponential horn, most of the sound goes out along the axis. Of course, we can hear a little sound all around, but over here in front, it should be very much louder. Let me listen. Yes, there's a good strong concentration right here. And so that you can hear what I hear, we've set up this special microphone. And we've mounted this meter near the mic so that you can see the changes in sound intensity as well as hear them. Now let's see what kind of beam this horn is giving us. First, we'll turn on the microphone. So, as you could see and hear, we've got a really good strong beam of sound to work with. Now let's put a reflector in the way. I'll put the mic over here first, and then push this baffle around to put the hard side in the beam. Now we have the beam of sound from the loudspeaker coming out in this direction. It strikes the central portion of the reflector and then goes off in this general direction. Let's try to locate the reflected beam. And to do that with some degree of accuracy, we'll use the microphone and meter, and then you can listen and watch at the same time. I'm going to move this back and forth through the general region where we expect the beam to be, and once we locate the center, we'll hang the microphone on the stand located at that point. Well, that looks pretty good. Let me just turn it on again for a moment and see if we really have it up near the top of the scale. Okay, so now we've located the reflected beam, and we know that it goes out in this direction and is centered approximately at the microphone. However, we're still assuming that the sound is going through this path and along this path to the microphone. Let's see if we can't check that more rigorously. And here's one way to do it. I'll use this as a shield and intercept the reflected beam. Of course, when I do this, the sound should drop and the meter should go down. And of course, I can also intercept the direct beam, or even put the shield right here where the two beams come together at the reflector. Well, I think you'll agree that's fairly convincing evidence that the sound is really traveling along these paths as we expected. But we haven't really asked the key question yet. Is this angle of reflection equal to the angle of incidence? Here's a quick way to find out. Looking past the microphone and into the mirror, you can see that the microphone lines up with the axis of the horn. So the sound and the light do follow the same path. Now let's sum up a bit. We've shown that sound travels in straight lines and reflects, and that the angle of reflection is equal to the angle of incidence. Now, of course, particles do this when they bounce off of a reflector. But also, waves behave the same way, as we've already seen with light and with water ripples. So which do we have here, particles or waves? Well, for one thing, waves bend around corners, whereas particles normally go straight ahead. Waves diffract. They spread out through narrow openings. and they spread in behind obstacles. And waves spread around the ends of barriers. We know from common experience that sound bends around corners. Let me turn this microphone on so that now you'll be hearing my voice only through this microphone. And I'm going to walk around behind our baffle and keep talking to you. Now, of course, you still hear my voice, though it's a little bit weaker. And this makes it obvious that the sound from my voice is indeed bending around this baffle in order to get back to the microphone. Well, from this point of view, it certainly seems clear that we are dealing with waves and not with particles. But there are many other characteristics of waves that you know about, so why don't we try to tie this question down more firmly? Now, a very basic test for waves is to look for an interference pattern. A good example of interference is a standing wave, such as we ought to be able to establish in front of this baffle. So let me pull it around. There, the baffle is now at about 90 degrees to the beam of sound from our horn, and we should be able to establish a standing wave here. But before we do that, let's go back and take a look again at a model of a standing wave. Now, if I send out a wave pulse, it reflects from the other end. And if I send out a continuous train of waves, the reflected waves interfere with the incident waves, and we get regions of maximum displacement and regions of minimum displacement. The regions of minimum displacement are the displacement nodes. Now let's see if we can get the same pattern in our beam of sound. We'll set up a tone on our oscillator, and this time we'll use a lower tone than we did before. Now we have our sound beam from the horn striking the baffle at right angles, and we want to explore the sound field out here in front. So we'll use our microphone and see if we can find maxima and minima. Well, clearly we have maxima and minima. Now let's measure the positions of these minima in the wave pattern. And to do that, I'll bring over a marker and place it along the axis of the sound beam and perpendicular to the baffle. And I'll turn the microphone on again. Well, I'm sure you'll agree that we had sharp nodes at these points that we've marked. The sound level dropped abruptly, and the meter went down to the bottom of the scale. So the evidence is mounting that we do have a standing wave here, that this is an interference pattern, and inevitably that sound is a wave phenomenon. Well, if so, there's some other things that we can check right away. For one thing, as you know, in an interference pattern, the dimensions depend upon wavelength. And in this special case of a simple standing wave, the distances between the adjacent nodes are equal to a half wavelength. So let's measure these distances. The first one is about 52 centimeters, and the second one is about 50 centimeters. Well, those are equal within the accuracy of our quick check. So we can take the half wavelength as having an average value of about 51 centimeters, which gives us a wavelength of about 102 centimeters, or lambda is 1.02 meters. We've already mentioned that the speed of sound in air is 340 meters per second. Now let's calculate the frequency. You remember the formula for frequency is equal to the speed divided by the wavelength. Incidentally, there's a nice way to visualize this formula physically. If you think of a train of waves going by you, and the length of that train that goes by in 1 second is simply the speed, then you divide that by the length of a single wave, and obviously you have the number of waves per second, or the number of cycles per second. All right, in this case, the frequency is equal to 340 divided by 1.02, and that is equal to 333 cycles per second. Well, we've calculated the frequency from our measurement. Well, let's see how this checks with the dial on the oscillator. This reads just over 33 times 10, so the frequency is set at just over 330 cycles per second. That checks very nicely. Now, what about this oscillator? Well, we can calibrate it independently. With an oscilloscope, it's very easy to spread the vibrations out in space using an appropriate sweep speed. For example, we established a tone of 1,000 cycles per second on the oscillator and selected a sweep of 1/100th of a second, and then counted exactly 10 vibrations across the face of the scope. Well, we did this at a number of frequencies, and the calibrations all checked out quite nicely. Now, if we select a higher frequency, what will happen to our wavelengths? Well, let's do that. Let's multiply the frequency by 10. To do that, we don't have to change the dial at all. We simply throw the range scale by a factor of 10. So now we've increased our frequency by a factor of 10. We should have cut our wavelength to 1/10. Let's mark the positions of the nodes with this higher frequency. I'll turn on the microphone. And let's count how many we have. Starting a little bit to the right of the mark we had before, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So again, within reasonable accuracy, we've obtained 10 nodal points, or 10 half wavelengths, where before we had just one. And this, of course, shows that our wavelength has gone down by a factor of 10 when we increased our frequency by a factor of 10. Now, one interference effect might conceivably be an accident. There's another familiar one that we can try. You've used a grating to obtain interference with light and with waves in a ripple tank. This is an interference pattern beyond the grating, a transmitted pattern. And this is the reflected pattern produced by a grating. Notice the antinode holding steady in this direction, and the nodes here and here. If we were to investigate this pattern along an arc like this, we would pick up regions of minimum displacement alternating with regions of maximum displacement. We would be observing a cross-section of this interference pattern. We can do a grating experiment with sound using a similar geometry. A grating, a source of sound, a receiver with which to explore along an arc about the grating, and a baffle to block direct transmission between the source and the receiver. Over here we have our source horn with the beam of sound coming off in this direction. And here we have a grating that we've made from dowels placed 15 centimeters apart from center to center. You can make one easily with some old broom handles. We've placed the plane of the grating at right angles to the beam of sound. And over here we have another horn, a receiver horn. As you see, we've inserted our microphone into the throat of this horn, and this gives us a sharply directional receiver to pick up the rather weak sound that's reflected from the grating, and also to discriminate against sound from other parts of the room. Now, this wire along here pivots the receiving horn about the center point of the grating, so that we can move this horn along the arc here and always keep it pointed right at the grating. Now let's set up a tone on our oscillator. And we've picked 5,000 cycles per second this time. Now let's start by looking for a maximum in the wave pattern. So I'll turn on the microphone. There we found a good strong maximum and marked it. But you noticed right near that maximum there was a secondary maximum. Now actually this is the sort of thing we should expect because we have a rather small grating. It's got only 7 elements, whereas an optical grating normally has thousands of scattering elements. And because of its finite size, this grating produces a secondary interference pattern that's superimposed on top of the primary interference pattern. The primary pattern is the one that's determined only by the spacing between the elements and the wavelength. So as I continue to explore this sound field, I'll try to pick out only the highest maximum and the lowest minimum. In other words, I'll try to mark only the primary interference pattern. Well, now you can really visualize this interference pattern produced by our grating. You see spread out along this arc two strong maxima and a sharp minimum or node in between. Actually, as you know, there's another minimum over here closer to the sound beam, but it lies right along our baffle, so you can't observe it. Now, that would be our first minimum. This is the first maximum. Over here is the second minimum, or second node, and out here we've marked the second maximum. This is a very well-defined interference pattern, but one that's quite different from the standing wave we observed in front of the reflector. So here we have strong, independent evidence that sound is a wave phenomenon. Now there's something you can calculate. This second node is located at an angle of 43 degrees from the axis of the incident sound beam. And that axis, you remember, is at right angles to the plane of the grating. And the elements of the grating are spaced about 15 centimeters apart from center to center. So from this information, you can calculate the wavelength of the sound we've just used. But also, you've got a new way to calculate the speed of sound. Remember, we used a frequency of 5,000 cycles per second. And using that number and the wavelength you've just calculated, you can find out the speed of sound in this room today. Now there's just one thing we've omitted from the usual list of wave properties. When waves pass from one medium to another, you often see a change of direction, a refraction. A change in the depth of the water in your ripple tank gave you a model of two different media. If you give the shallow area a special shape, a lens shape, the refraction of waves through the lens produces a focusing effect on the waves, concentrating them in this small region. With this double convex lens, we're going to try to refract sound, to focus sound waves. This lens is made of carbon dioxide gas coated on both sides with thin plastic sheets. The carbon dioxide is pumped up to a little more than atmospheric pressure in order to maintain the shapes of the lens surfaces. Our beam of sound is directed at the center of the lens right here, so we expect to find the focus out in this direction. Let's use the frequency of 5,000 cycles again. The screen here is almost perfectly transparent to sound, and it's located right where we expect to find the focal pattern. So let's explore this region with our microphone and observe the changes in sound intensity as we go through it. Now, just so we can keep a record of what we observe, each time the meter needle reads 70, I'll put a marker on the screen. Everywhere within this circle, the meter reading is more than 70. Well, that looks like a satisfactory focal pattern, but how can we be sure that we aren't simply measuring the cross-section of the beam directly from the horn? I'll hang the microphone here at the center of our focus and then go and take the lens away so that nothing will stand between the loudspeaker and the microphone. And while I do this, you watch the meter. Well, our lens works. We've observed the refraction of sound through carbon dioxide. Now, what have we learned about sound? We've seen that the angle of reflection equals the angle of incidence. We've heard the diffraction of sound around the edge of a barrier. We've observed the interference pattern in the standing wave in front of a reflector. And we've noted that speed equals frequency times wavelength for sound as it does for other waves. We've observed another interference pattern of nodes and antinodes produced by a grating. And here we've observed the refraction of sound. So now we know that sound is transmitted by waves and that its behavior is predictable by the same wave theory we've already learned.